Hello again. We're back. We're better than ever. We're ready for section 4 of chapter 1, titled Linear Functions. Now, I'm going to divide this section up into two parts. This is a rather long section, okay? So you want to sit back, relax, get ready to take your notes, and stay focused. Resist the urge to let your mind wander off into la-la land. Okay. We're going to start off with a definition. We're going to define the word function. A function is a dependent relationship between two quantities, or between quantities, where each independent variable, and the independent variable is always your x variable, corresponds to, and this is important, exactly one dependent variable, and this variable is usually y. So y always depends upon x. For example, the speed at which you drive your car to school. You know, if you drive slow, well, that gets pumped through a function machine. We'll call that function machine some machine f. It results in a certain time. That's your y variable. Or another way to say y is f of x. F of x. You need to make that note. If you drive slow, well, then it takes a long time to get where you're going. That's the output. But if you drive fast, all right, then what does your function do? Well, the result or the output would be it takes a short time to get to wherever you're going. All right, note, f of x is really just y. They say the same thing. All right, we say a function in terms of x. You have inputs, you have outputs. For example, if your input's a chicken egg, all right, and you pump that chicken egg into an oven, that's your function machine, then what pops out? What's your f of x? Well, it'd be a chicken, right? So let me draw you a chicken here. That's all I got. That's a chicken. It's not a duck. Don't tell me it's a duck. It's a chicken. Okay? Anyway, the input are the eggs, your x's, and the outputs are chickens. Now, I have a cute little YouTube video that I'm going to show you in class, so remind me about that. Oh, let's talk about a couple real quick examples. Here, for instance, if toothpaste costs $2 per tube, then we would say that the price or the function in terms of the amount of tubes you buy. So the price of one tube would be $2. Does that make sense? Here's your x, your input. Here's your y, or your f of x, or in this case, your p of t, I guess, your price in terms of tubes. If a ball goes 20 feet per second, then we could say, okay, the height, here our function is height, the height at 3 seconds would be what? Well, 3 times 20 would be 60 feet. All right, again, time here is your input, and height, or feet, is your output, your x and y. Another way to think of it would be t, and this guy would be h of t, the height in terms of the time. Need to get used to this notation. Okay, a couple special functions that we're going to talk about here. The first one are square root functions. Okay, here's the square root symbol. You guys have seen that before. All right, now think about what kind of numbers you can take the square root of. Square root of 25? Well, that's 5. It's pretty easy. But what's the square root of negative 25? Uh-oh. If you try to type that in your calculator, what do you get? You know what you get? You get a really, really mad calculator, because it says, what are you doing to me? What are you? I can't do the square root of negative 25. So put a little frowny face there. All right? You can't take the square root of negative 25. It can't be done. So we say that a square root function has a restriction on its outputs, or I'm sorry, on its inputs, and also its outputs. So what are the possible inputs? What kind of numbers are you allowed to take the square root of? you're allowed to take the square root of positive numbers. Positive numbers. Also 0. Okay? And what are the possible outputs? In other words, the possible y's. Well, square roots are also always going to be positive. Now, if it was cube roots, well, then that'd be a different story. So positive and also 0. The square root of 0 is 0. Right. What about absolute value functions? Absolute values are denoted with 2 sticks and something inside. Absolute value of negative 2. How far is negative 2 from 0? It's 2. Absolute value of negative 3 is 3. So what are the possible inputs? What kind of numbers are you allowed to take the absolute value of? Well, you could take the absolute value of anything. So we say that the possible inputs are all real numbers. Any real number. There's a symbol. It's an R. It's got a little crutch. Okay, that's the all real number symbol, and we'll use that from now on. But what are the possible outputs? What kind of numbers could you get out of a square root function? I'm sorry, not square root, but absolute value function. Well, absolute value functions only yield positive numbers. So we say, oh, well, only the positive real numbers. Okay, only the positive real numbers. And 0, the absolute value of 0. Okay, so you see there's a restriction on the output. A fancy way to say that is a restriction on the range. And speaking of range, we're going to move to our next slide where we have a few more definitions. Now make sure you guys are pausing the video here to give yourself time to copy down these definitions. I know I'm moving through them rather quickly because I typed them out in advance. But that's the nice thing about the flipped classroom is you can pause the video and rewatch and go back. Really cool. All right, anyway. So, a couple definitions here. The possible inputs, i.e. the x values. The x values of a function are noted as the domain of the function. It's the set of values over which a function is defined. And that's a cute way to say that the numbers you're allowed to plug in. For instance, with a square root function, we can plug in positives and be happy. So, make him happy. But we plug in negatives, and you know what? We're sad because we can't do it. All right. And then the possible outputs, it's not the domain. What's it called? That's called the range. All right. The possible outputs are the range. Okay. Now, there's an easy way to tell if something can be a function or is a function or not. And it's simply this. The domain, in other words, the x values, cannot repeat. X's can't cheat. You got me? X's cannot cheat. So let's do a couple quick examples here. Let me blow this guy up. Here's number 1. Let me move number 2 out of our way. Is this a function? Yes or no? Does the domain repeat? Let's see here. 2, 4, 6, 8. Well, it doesn't. So you know what? This guy's a function. So just put function right there. He's good. All right, cool. Let's get rid of number 1. And let's bring up number 2. Is he a function? Well, let's see here. The domain has 3 elements, 2, 3, and 4. In other words, there are 3 x's. Do any of them repeat? 2 goes to square root 12. 3 goes to square root 7. 3 also goes to negative square root 7. Uh-oh, we got a cheater. At 3, he's 2-timing those square root 7s, isn't he? One day he's with the positive square root 7, the next day he's with the negative square root 7. That ain't good. He's not allowed to do it. So, we say that this is not a function. Not a function. Because the 3 has 2 y's. The 3 has 2 y's. Positive root 7 and negative square root 7. Okay, so that's number 2. Let's get rid of him. Move him off to the side. And let's bring up number 3. So copy that one down. Is that one a function? Well, let's see here. The domain has 4 elements, and they all get mapped to 4. But does that meet the definition of a function? Do any of the x's repeat? No. Now the y repeats, but that's okay. All right, let's think about what this graph would look like. 1 would go to 4. 3 would go to 4. 5 would go to 4. None of those x's repeat. Only the y repeats. This is technically a horizontal line if you kept mapping, every single different x value possible to y equals 4. But the point is, each x has exactly one y. It's the same y, but that's okay. So this one is a function. Now I sketched that picture, and I hope you did too, because I want to introduce something. And you've probably seen this before. It is the vertical line test. Okay, any vertical line can only pass through a graph one time, in order for the graph to be a function. So for instance, if I give you, a fun little curve like that, okay, is that a function? Yes or no? Well, sketch some vertical lines through it. Does it only touch once? Yuppers. Does it only touch once there? Yuppers. So this one, we'd say, is a function. That red curve is a function. However, if we drew a curve, let's take our S and draw it vertically like that. If we draw a vertical line such that it's about at x equal 1, looky here, boom, 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 crosses 3 times. That means that the x value repeats for multiple y's. Whatever x that is, it looks like it's about x equal 1, is a cheater. So this guy is not a function. Alright, that's the vertical line test. You've seen that before. You probably saw it in your Algebra 1 class and maybe even your Algebra 2 classes. Alright, let's do some algebra, shall we? We'll come back to pictures later. I'm going to give you a function. Here it is. If f of x is equal to x squared plus 4, that's a quadratic function. It looks like a parabola. I want you to find f of 3. Say that with me. F of 3. All that means to do is evaluate this function at x equal 3. Take that 3, that's your input, plug it into your function machine, f, or f of x, which is really x squared plus 4, and see what you get out. See what happens. See what f of 3 is, your output. Well, so let's do the work over here. F of 3, everywhere you see an x, just put a 3. You have 3 squared plus 4. Order of operations says to do 3 squared first, which is 9 plus 4. And 9 plus 4 is 13. So your output would be 13. Therefore, we just say that f of 3 is 13. Here's your x, here's your y. It's an ordered pair that would be on this graph if you were to graph it. Alright, you could just start plugging in a bunch of numbers and get a whole bunch of ordered pairs and play connect the dots, and it'd be really, really pretty and really, really fun. You can do it in your own time, though. We gotta move on. Okay, I want to shrink some of this stuff and give myself a little bit more room. And we're going to do a couple more of those just for giggles. Do the same thing with f of negative 2. With the same function that we just had. F of x is equal to x squared plus 4. So wherever you see an x, put a negative 2. Now, put the negative 2 inside of parentheses. I cannot overemphasize that enough. You will get in trouble if you don't put parentheses where you should, because your calculator is not smarter than you, believe it or not, and your calculator won't know what you're trying to say if you don't put those parentheses. All right, well, 2 squared is just 4, and 4 plus 4 is 8. What if you did, f of, I don't know, junk? Just some junk. That means wherever you see an x, you replace it with what? Well, you replace it with junk. And you say, wow, this is what I'm talking about. This is what math has been like for the last 10 years. It's just been a bunch of junk. What if you had f of the quantity x plus 1? That means wherever you saw x, you replace it with x plus 1. Now remember, I said put everything in parentheses. Alright? And then put up plus 4. Now, guys, don't worry about the left side of these equal signs. Don't let that confuse you, okay? I know that that's pretty common. Now, be careful here. If you have a quantity squared, that means you need to do FOIL. You need to write it out 2 times and do FOIL. You're going to end up with x squared plus 2x plus 1. If you're not sure where I got that, put x plus 1 times x plus 1 and do the distributive property? Is that coming back to you? I know it's been a long summer, but hopefully that's coming back to you. There's still a plus 4 sitting there. And then all you would do is combine like terms. X squared plus 2x plus, oh, I made a mistake here, didn't I? I forgot. When I do x squared, x plus 1 quantity squared right here, it should be x squared plus 2x plus 1, and then the plus 4 is still there. So 1 plus 4 actually becomes 5. That would have been the answer. Sorry about that. Okay, so I want you to put a star next to this picture that you're about to sketch, because this is a really, really crucial picture. And I'm going to introduce a concept here that kids just have a really, really difficult time with, and it's a really, really important concept to grasp. And the earlier you do, the better off you're going to be this year. Okay, and that's determining the domain and range from the picture, or from a picture of a graph. So if here's the x-axis, okay, and here's the f of x-axis. Now remember, that's really just the y-axis. They mean the same thing. Sketch the graph of some random quadratic equation, all right, and that end up looking like a parabola. Okay, you've seen those in Algebra 2 and Algebra 1. What's the domain of that function? In other words, what possible x values are included on that curve? Well, that curve is going to go forever to the right and forever to the left. It's never going to stop going right and left. It's going to keep going forever and ever and ever. It's going to keep going forever to the right and forever to the left. That means the domain has no restrictions. And when the domain has no restrictions, we put, oh, well, the domain is all real numbers. Now, there's a cute little way I want you to start writing domain. Put bracket, domain always has the x values, all x's, such that, so just a vertical line, such that it's all real numbers. Remember, that's what domain is when it goes forever to the left and forever to the right. But the range on this one, well, it's a little bit different. It's got restrictions. Okay? The range are all the y values that are included on the graph. In other words, think vertically when you're thinking about the range. Now, the graph, it goes up forever, doesn't it? The graph goes up forever. Oh, sorry, I didn't mean to do that. The graph is going to keep going up and up and up, up and up and up, but doesn't it go down forever? No, it comes down and it bottoms out right here, right there at the origin. Well, what's the y value at the origin? Well, the x value is 0 and the y value is also 0. That means the range is restricted to y such that y must be bigger than or equal to 0. That's the range of that function. The domain's all reals. You can plug in whatever you want, but the domain, or the range, is greater than or equal to 0. Well, let's try this with a linear function. Okay, so if I give you some function, 20 minus 5/8 x. First off, I want you to just find f of 16. That means wherever you see an x, substitute 16. So 5/8 times 16. When you multiply fractions, cross cancel if you can. So 8 becomes a 1, 16 becomes a 2. This really just says 20 minus 10, and 20 minus 10 is 10. So when you plug in 16, you get 10. Now if you were to sketch the graph of this function, its y-intercept would be way up here at 20, and its slope would be negative 5/8, or down 5/8. Well, I'm not going to bother actually sketching that perfectly. The point is it goes down 5 and right 8. I want to know what's the domain and what's the range. What's the domain and what's the range? Now the domain has to do with the numbers you're allowed to plug in for x. Is there anything you're not allowed to plug in for x? Well, the answer is no, there's not. That means the domain is all real numbers. That means that this blue arrow goes right forever, and this one goes left forever. Now what about the range? Does this arrow go down forever? Yep. Does this arrow go up forever? Yep. That means the range is also all real numbers. And I didn't write it with the nerdy notation. I apologize for that, but I was running out of room on the side of that page. In fact, all linear functions, unless they're constant functions, will always have a domain and a range of all real numbers. Well, let's move to restrictions. And here they are. Okay, this is number 6, part A. And it says f of x is equal to the square root of x minus 3. Now we're getting saucy. Okay, so what I want you to do is find the domain. What values are you allowed to plug in? You might want to make that note here. What values, and this is talking about the domain here, am I allowed to plug in? What can I plug in? Well, here's a little hint. Take whatever in the square root and set that equal to 0 and solve that for x. And you get 3. Guess what? That's where your domain is going to begin. Make a little table right here. X comma y. Start with 3. When you plug in 3, what do you get to this function? 3 minus 3 is 0. Go backwards. Plug in 2. Well, 2 minus 3 is negative 1. Uh-oh. Frowny face. Can't do it. Can't take the square root of negative 1, can you? Alright, plug in 4. 4 minus 3 is 1. Square root of 1 is 1. Plug in 5. 5 minus 3 is the square root of 2, which is not very pretty, but at least it's real. Plug in 6. 6 minus 3 is 3, and the square root of 3 is just the square root of 3. Plug in 7. 7 minus 3 is 4, and the square root of 4, well, that's nice and pretty, that's 2. Alright, what I would suggest doing is do a little sketch here of all these points. 1, 2, 3 gave us 0, 4 gave us 1, 5 was kind of nasty, 6 was kind of nasty, 7 gave us 2. There you go, that's what a square root graph looks like. Notice, the domain is the x column, and the range is the y column. The x column starts at 3, and it gets bigger. Where does the y column start? It starts at 0, and it gets bigger. All these numbers are gradually getting bigger. 1, then square root 2, then square root 3, then 2. Folks, that's your domain and range right there, just from the table. Or you can get it from the graph. So let's write our domain. Our domain is all x's such that x has to be bigger than or equal to 3. It's not allowed to be smaller. If it is, the world blows up. The world falls apart. Alright, and then the range. All the y's, or f of x's I should put, such that y has to be bigger than or equal to 0. You'll never get a negative square root. It's just not going to happen. Okay, cube root, different story. Okay. Let me take, I didn't want to do the whole picture. I just want to do part of that. Well, oh well, okay. Let's do part B. Let me switch colors to make it a little bit more noticeable. I want you to sketch a curve here. Draw yourself an XY axis just like I have. Put a point at negative 2, 2, just like so. Put a point at 3, 4. 1, 2, 3, 1, 2, 3, 4. Just like this. I want you to kind of do one of these doodads. Right there. Okay? I want you to tell me the domain and the range. In other words, where does the domain begin and where does the end, and where does the range begin and end? Okay, do you want to do domain or range first? Let's do domain. The domain has to do with the x values. X values. Okay? So where does x begin and where does x end? Well, here's negative 2 and here's 3. It looks like the x's go from negative 2 to 3. So we would say that, okay, the domain is all x's such that it starts at negative 2, smaller than all the x's in between, and it finishes at 3. Now I want to make a little adjustment here. This last circle was actually supposed to be an open circle, which is why I didn't put the equal sign underneath the less than there for the 3. My apologies. Okay, now let's talk about the y values. Now we're speaking in terms of up and down. So watch this. You got to make those sounds when you draw on those dashed lines. Okay, how far down does y get? The lowest it gets is 2. How far up does it go? The highest it gets is 4. So we would say, okay, the range is all y's starting at 2, including everything in between, and finishing at 4. That is the range. Notice I didn't put less than or equal to 4, just less than 4, okay, because that was an open circle. All right, just 2 more slides, guys, and we'll be done for part 1. All right, another definition I need to throw at you. That's a linear function. And this is a minor adjustment. Instead of just y equal mx plus k, it's f of x equals mx plus k. That's a linear function, a function that looks like a line. Okay, so what I want you guys to do is find f of 1 for the function 3x minus 5. That means wherever you see an x, replace it with 1. So 3 times 1 minus 5 is 3 minus 5. Answer, negative 2. Very cool. So we have an ordered pair now. When we plugged in 1, we got negative 2 for an output. Very cool. You can even make a sketch if you wanted to. Let's hold on 1 second. I don't want to do the sketch yet. Let's find f of 4. Okay, so f of 4, wherever you see x, put a 4. 3 times 4 is 12, and 12 minus 5 is 7. So that's an ordered pair, 4, 7. Now, you've got 2 ordered pairs that satisfy this linear equation. Well, you could make a sketch now. Put those 2 points, 1, negative 2. There's a dot right there. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Right about here. And there you go. That's that line. Now you could have just graphed it right away, right? Because you know how to graph a line in slope-intercept form. But the point is, you can also sketch the line using points that satisfy this equation, this set of circumstances. 3 times 1 minus 5 is negative 2, and 3 times 4 minus 5 is 7. And there's an infinite amount of other possibilities. Okay, last example. Alright, here it is. So let g, or g of x, you can think of it like that, be a linear function such that g of negative 1 is 4 and g of 3 is 12. Find an equation for g of x. Now what this means is when you plug in negative 1 to some function, you get 4. And when you plug in 3 to some function, you get 12. Those are x's and y's. They're ordered pairs that satisfy this g of x, whatever it is. Now the key is we know it's a linear function, which means it must take this form. It must take the form f of x. Oh, we're using g, aren't we? G of x equals mx plus k. Now, do we have enough information to find m? Do we have 2 ordered pairs? Well, here's negative 1 comma 4, and here's 3 comma 12. We sure do. Just do y2, 12, minus y1, 4, over x2, 3, minus x1, negative 1. That's 8 over 4. Answer, 2. 2. So we know m is 2. Now, do we know the y-intercept yet? Well, not yet, but we can just pick one of our points. Why don't we just use 3, 12 right here. Plug in 12 for g of x, or y, equals 2 times 3 plus some k. So 12 equals 6 plus some k. That means k is equal to 6. So now you can write your function. Now, instead of y, we're growing up. We're nerds now. We're smart nerds, though. We're cool nerds, I should say. We're going to use g of x instead of y. So g of x equals mx plus k. But what is m? M is 2x plus, what's k? Okay, is 6. And there you go. There's the equation of your line in slope-intercept form, but instead of putting y, you did the cool nerd thing, and you put g of x. You left it in function notation. You are one cool nerd. Hey guys, it was fun. That's part 1. We'll do part 2 later. Hope you enjoyed it. I'll talk to you later. I'm out.